Hi everyone, I made just a small mistake on my first video with the positives and negatives. So where I left off in the first video, the first video of this example, I should say, where I left off was I was performing the first derivative test. So I took the first derivative, set it equal to 0 to find the critical numbers. We got one critical number and that was at approximately 0.61. So now I need to go through and create a number line with this critical point and take note of where my original function is undefined. So going to make a number line, right? I only found one critical point and that was e to the negative 1/2, which was at approximately 0.61. Okay, and then notice that in this original function, which I've discussed already, that we have the natural log. So with a natural log function, it's not defined at 0 and it's not defined at any negative x values. So I know I have to stop this number line at 0. So I'm stopping this number line at 0, and that's because, since ln of x can't be 0 or negative. All right, so I have to stop the function there because that's where it is not defined. All right, so from here, what I'm going to go through and do is use the intervals from my first part of this to test each side of the 0.61 and figure out what's going on there. So you can choose anything you want. It just needs to be one thing on each part of this number line. So in between 0 and 0.61, I know 0.5 is there. And I'm just picking 0.5 because I think it's easier. You could have picked 0.1, 0.2, 0.3, 0.00123, many things, but 0.5 seemed like the easiest thing to work with, so that's what I chose. All right, so now I need to plug this into the derivative. So f prime of 0.5 is equal to, go up here to find my derivative. So let's see, I had x times 2 ln x plus 1. Okay, I don't care what this is equal to. I only care if it's positive or negative because we know that that tells us a lot about if something's a local max, min, or an inflection point. All right, so if I have positive 0.5, I know this x is positive, and I'm multiplying it by 2 times the natural log of 0.5. Okay, the natural log of 0.5 is negative 0.69. If I multiply by that by 2, I get a negative 1.386. Adding 1, I'd get a negative here. So a positive times a negative is a negative. That means in this area of the graph, my first derivative is negative, so I know that it's decreasing. So it's going to look something like that. Obviously not exact, but it gives us an idea. So our first derivative is negative there. All right, next I need to test a number on the other part of this interval. So that would be over here. And I'm just going to pick 1 again because I think it's the easiest thing to choose. So I'll take f prime of 1, which will be, let's see, oh, I didn't plug this in here, sorry. This first one, this should be 0.5, this should be 0.5. I said it verbally, didn't write it in there. Okay, so f prime of 1 is going to be 1 times 2 ln of 1 plus 1, which gives us a positive times a positive, and that's a positive. So here, I know my slope is increasing since the derivative is positive, right? And now this allows us to figure out on what intervals we're increasing and decreasing. So, I'll write my final answer, okay? From 0 to e to the negative 1/2, I know the function is decreasing, and that's because my derivative is negative in that part. The function is decreasing. All right, looking on the other part of that, since my derivative is positive, I can say the function is increasing from e to the negative 1/2 to infinity. All right, so thinking about the endpoints here, I know I can't include the 0 or anything after because my function isn't defined at 0, so that's why I have a parentheses. I wouldn't include the e to the negative 1/2 because my derivative there is 0. that means this function isn't increasing or decreasing at all. It's just constant, right? It's that horizontal constant line. Okay, and then similar idea for the increasing part. I know I can't include e to the negative 1/2 because my derivative is 0 there, which means the function is holding constant. And then for the end part of this, if it's going off to infinity because I'm not limited at all on the right side, I would of course use a parentheses rather than a bracket there. All right, sometimes people will ask, oh, how do you know, like, something different isn't happening at 0.1 or 0.2 or over at, 0.6? That's because if this weren't decreasing the whole time, I'm going to erase this in a minute, but let's say it's decreasing, decreasing, decreasing. Okay, in order for it to be increasing again, I would have to make a turn, which means I would have another critical point there. So that's how I know it has to have that same pattern for that whole part of the graph. All right, so now I'll use what we have above to determine if our critical point is a maximum or a minimum. So for this, notice in my picture, I go from decreasing to increasing, and that tells me that I have a local minimum. All right, so we have a minimum, and that's because the function goes from decreasing to increasing. Okay, so I answered part A and part B just using the first derivative for both of those. Now for part C, notice that, I'll scroll back up there, it asks me about intervals of concavity and inflection points. So we should remember, oh yeah, the second derivative is really helpful for that. So now what I'm going to go through and do is use a similar process but with the second derivative. And for this, I actually recorded this video once, but I made that small mistake. So the writing is still in here, but I'll explain all of the writing that I have. Okay, so for part C, like I said, we need the second derivative, right? I re-recorded the first derivative just so we would have it here. Took the second derivative of that, so taking the derivative of the first part, the derivative of 2x is 2 times ln x plus 2x is my first function times the derivative of the second is 1 over x. So I just used the product rule on that part there. Now the derivative of x is 1, simplifying that a little bit. Okay, the 2x times 1 over x has the x's dividing out to 1, so I have a 2 left there, plus 1 is 3. Now I need to set that equal to 0 and solve. When I do so, when I subtract the 3 and divide by 2, I get negative 3/2. And from there, if I exponentiate both sides by e so I can undo this natural log here, I'm left with x equals e to the negative 3/2, which is about 0.22. All right, so from here, I need to figure out if this point, if this critical number gives me anything special. Really what I'm looking at is this an inflection point or is it not? And I also want to determine those areas of concavity. So I'm going to create a number line just like I did with the first derivative. Here I have to start it at 0 because my original function isn't defined at 0 or beyond that. And then I want to explore the intervals that I have set up here. Okay, so the first interval we'll look from is from 0 to e to the negative 3/2, or you could say about 0.22, and 0.1 is in there. So if I plug 0.1 into my second derivative, I see that I get a negative. All right, so remember, second derivative being negative means that I have something that is concave down. All right, so I know this part, concave down. All right, second. Okay, 1 is after the 0.22 and easy enough to plug in, so I just use that. If you plug 1 in, you get a positive. So my second derivative is positive there. All right, so now we can conclude that from e to the negative 3/2 out to infinity, since my second derivative is positive, I know my graph is concave up. All right, from 0 to e to the negative 3/2, my second derivative is negative, so I know the graph is concave down there. And also recall that when we switch from concave down to concave up, or from concave up to concave down, we have an inflection point. So that means we have an inflection point at e to the negative 3/2. All right, so sorry I didn't write there, but hopefully the verbal explanation helped a little bit. Please ask any follow-up questions you have on the notes on the appropriate discussion board tab. Thank you.